Today we're going to wrap up Trig Unit 1. It's day 6, and we're going to do a few things. We're going to find the length of an arc. We're going to define sector of a circle and find area of a sector. You may have done this last year in geometry. When we did it in geometry, we used degrees for all our measures. And as we talked about at the beginning of this unit, we're going to start to transition to use radians. So normally arc length and sector area is done using radians, and so you'll see that you're going to get two different formulas depending on whether your angle that we're working with is in radians or degrees. So let's look. We can calculate the length of an arc if we know the measure of the central angle intercepting it. So let's look at this picture here. Here's a circle. And here is an angle. This is our terminal side. This is our angle. So this would be our central angle. This is the initial side. So what's the arc? It's the length of the outside of the circle in between the initial and the terminal side. So that has a length in units. And of course this goes from the middle of the circle to the outside. So this right here, and I'm unfortunately using the same color, this right here is our radius. So if we want to figure out the length of this arc right here, we need to have the central angle and the radius. And the formula is here. If the angle measure is in radians, so if our central angle is in radians, then the formula for calculating the arc length is just theta times r, where theta is the angle measure, central angle measure, in radians, and r is the radius of the circle. So pretty straightforward. Since the standard is to have arc length and sector area in radians, if your angle is in degrees, not radians, the formula is a little bit different. And the other thing I didn't mention here, S is normally what we use to stand for arc length. Don't ask me why. S isn't in arc length at all, but that's what you're going to see on the worksheets for standing for arc length. Okay, so in degrees, you'll see the theta, which is our central angle, and r, which is our radius. What's added? Well, the conversion factor here. So remember, this converts degrees to radians, so we're just going to take our angle, convert it to radians, which is what this piece here does, and then multiply it by the radius. So that's the only difference. You just have to make sure you use the right formula depending on what your angle measure is, whether it's degrees or radians. So here's an example, and if you're not told, again, if you don't see a degree sign, then it's radians. If I tell you it's degrees, then you should assume it's degrees. If I tell you it's radians, you should assume it's radians. Otherwise, if you're not told, if there's a degree sign, it's degrees, else it's radians. So theta is 2 pi over 5, radius is 10 inches. So this is going to be in radians. So I'm just going to plug the two parameters into the formula, multiply. So again, we just multiply the top by the 10 and 5 by 1. You're going to get 20 pi over 5, or 4 pi inches. So if I tell you to leave it in terms of pi, you can leave it like this. Otherwise, you can go ahead and multiply it in, and normally it should tell you round to the nearest tenth or hundredth or whatever. So this is in linear units or inches. Second example, I have my angle in degrees, 30 degrees and 15 centimeters is my radius. So I'm going to use the second formula. 30 times pi over 180 times 15. So I'm going to multiply all the tops together to get 30 times 15 times pi divided by 180, and that will give me 2.5 pi centimeters. If I asked you to round it to the nearest tenth, you would multiply pi by 2.5. Pretty simple and straightforward. You just have to know the formulas. All right, you should try this one. So 3 pi over 8 is your central angle, radius is 7 meters. And then I'll give you a minute to try that. Here's a solution. Here is an example using degrees. Whoops. So you should be able to do both of these. All right, so we're going to move on now to sector area. The pie-shaped area formed by an arc and the central angle is called a sector. So here you can see I have my terminal side, I have my arc. So this is the piece of pie, this is the sector. And we want to find the area of that sector. And we have the same things that we had before. We have a central angle, theta, and we also have our radius, which is this length here. So the formula for calculating sector area, if your angle is in radians, is pi over 2 r squared, or not pi, theta over 2 r squared. So it does actually look a lot like the area of a circle, except you're only taking a portion of that circle. What portion is going to be defined by your angle divided by 2. So again, theta is your central angle and r is your radius. If your angle's in degrees, you might already guess what what's the difference. It's going to be that same formula with just the conversion factor included. So theta over 2 times pi divided by 180. Again, this converts your angle from degrees to radians times r squared. And if we kind of multiply that all together and simplify it, you end up with theta pi r squared over 360. That's the simplest form of the formula for sector area if you have your angle in degrees. Example. So I have a theta or an angle 2 pi over 5. My radius is 10 inches. Plug them into the formula. Oops. So what did I do here? I just 2 pi. This essentially is just theta times 1/2. So if theta is 5, I'm going to multiply it by 1/2, and that's going to give me 2 pi over 10. So 2 pi over 10 times 10 squared is going to be 2 pi times 100, which is where I get 200 pi over 10. Simplify this to get 20 pi inches squared. So areas are always in inches squared. And then if I had asked you to round it to the nearest tenth or hundredth, you would go ahead and multiply this in your calculator. All right, here we have an example for sector area where our central angle is in degrees and our radius is 15 centimeters. So we use the second formula, central angle times pi times our radius squared divided by 360. If I multiply everything on the top except pi, you're going to get this, and then divide out the 360, and you end up with 18.75 pi centimeters squared, which, again, multiply it if I ask you to round to a decimal. All right, so you should find the sector area for these two problems. So this one is has an angle in radians, and this one has an angle in degrees. All right, there is one more thing I want to do. No, actually there's a couple more things we want to do. So first thing we're going to do is we're going to use the formulas but not in straightforward form. We're going to have to maybe use the formulas to find the radius or something additionally. So let's look at the first problem. Find the sector area if the arc length is 8 centimeters and the radius is 10 centimeters. So remember, sector area is, well, we don't have the central angle, but it's going to be theta over 2 times the radius squared. We have the radius. What we need is theta. How are we going to find theta? Well, we have the arc length and we have the radius, so we can use the arc length formula, which is S is equal to theta times the radius. So we're going to plug in what we have. We're going to plug in 8 for the sector area, 10 for the radius, and solve for our central angle. So as it says, work backwards from the arc length to find the central angle. That's our formula. Plug in what we have. We're going to divide both sides by 10 to get a central angle of 8/10 or 0.8. Now we can plug that in to our area formula, and it's going to be in radians. This will be in radians unless, since we used the radian formula for arc length, so we can just plug it right into the radian formula for sector area. So 0.8 divided by 2 times radius squared, which is 10, and you end up with 40 centimeters squared. So you had to do a few steps to get to the information you needed to find the sector area. Next example, find the radius if the sector area is 120 centimeters squared and your central angle is 2.2. And since there's no degree signs, you have to assume it's radians. All right, so this is a little funny. I'm not sure why this is here. That's what we want to do, is find the radius. So set up our formula. Our formula is area is equal to theta over 2 r squared. We know that 120 is our area, so we're going to plug that in here. We know our central angle is 2.2, and then we're going to solve for r. Multiply both sides by 2, and now divide out our 2.2 and square root. So we're going to get our radius as 10.44 centimeters. Okay, now I think I have one for you to try. So given the sector area is 250 meters squared and the radius is 10, you should find the central angle. Go ahead and try that. The solution is going to be revealed as I get on to the next section. So there's one more example, and the problems in this presentation are strictly mathematical, but these problems are actually very application oriented. So we're going to be doing a lot of application problems using these formulas. And one of them is, most of them are pretty straightforward, but one of them is a little bit tricky. So it says Seattle is at latitude 47.6 degrees north. So think of it, we're on a globe, a rounded globe. So here's Seattle. Here's the center of the Earth. Portland, so this is 47.6 degrees. Portland is here at 45.5. So we basically have this, it's kind of like a sector. So if the radius of the Earth is 6370 kilometers, so this is 6370, so that's our radius length. Find the distance between the two cities. So where's the distance? Well, the distance is this, which is nothing more than our, let me get a different color, nothing more than our arc length. So basically, this is a problem that asks us to find, it says nearest mile, so I was off on this. It should be the nearest kilometer. This is just an arc length problem. So we need, notice first of all, our angles are in degrees, so that means we're going to use the theta pi r divided by 180. We have to use our conversion factor. We have our radius. We don't have our theta. We need to calculate it. Our theta is here, and all it is the difference between this latitude and this latitude. So to find our angle, we just subtract the two degree values. So this is going to be theta. And now we're going to plug it into our arc length formula. So theta times pi over 180 times our radius. It's going to be 13,377 pi divided by 180. We want it to the nearest kilometer, so we're actually going to end up putting it into our calculator. And again, I changed units. You should get about 233.5, which if I round to the nearest kilometer is 234 kilometers. So I think that wraps up this lesson and this unit. Bring your questions to class and you'll get a worksheet for homework.